Okay, everybody. This week for Chapter 4, we're going to be talking about water and water in the atmosphere. There's a lot of important concepts that you're going to need to understand for this. So I'll go over them, touch on them here in the different parts of the lecture, but you should pay close attention to their description in the text, and also make sure you watch these videos on the that are in the weekly modules, okay, because they'll go into everything in a lot more detail than I'm going to go into them in our lectures. So let me go back over to share screen, and we can get going here on the PowerPoint. So here's just some introductory stuff I'm going to go over real quick, and then we'll get into the heart of the lecture. Water is part of what we call the hydrologic cycle, the water cycle, which is the movement of water through the atmosphere, the hydrosphere, the lithosphere, and the biosphere. And that movement creates our weather. Now, this is an important distinction. Water is short term. It's like a snapshot of the minute, of the hour, of the day. It's the day-to-day condition of the atmosphere, whereas climate is the long-term average, over decades of weather conditions and extremes. And then meteorology is a scientific study of the atmosphere. So make sure you know the distinction between climate and weather, because that's for sure going to be on your test. All this is in the text, so I'm not going to spend a lot of time on it, but just keep in mind that, again, that water covers about 70% of the Earth's surface, and that the oceans contain 97% of all the water on Earth. And that's important for some reasons that I'll get into later. You look at that 97%, only 3%, about 3% of the water is fresh, and out of that, almost all of that is in ice and glaciers. About almost 100% of this is in ice and glaciers. So where we get a lot of our water, of course, is through groundwater for drinking and so forth. Okay, so again, this is just in the text. So make sure you familiarize yourself with these graphics and so forth. Okay, and how meteorologists, the people who study weather and climate, how they create their models and all the different variables that they use. Some of which we've already talked about, like barometric pressure, for example. This is what we're going to get in today: is pressure tendencies. Okay, and meteorologists, they collect all this material from all kinds of different sources. And again, if you just turn on the Weather Channel for 5 minutes, and you'll see all this, how they get all this incredible information, through radars, through basic things like this. You'll see these all over. We have them on campus, actually, and you'll see these that collect the wind speeds and wind direction and send it down to a little data collector, which in turn sends it off to the computers at school and so forth. They have things that rain, tell you how much rain and how much per hour and so forth. Okay, and then all this allows people to create the weather maps that allow for forecasting, whether it might be for the day or for the week or even up into 10 days. And you can see things here that we've already talked about with our high pressure or low pressure systems. Remember, 1013 is normal, so you can see that this is a pretty massive low pressure system right through here. And then we'll get into fronts in a later chapter, which is what these lines are right here. Okay, but the main thing we want to talk about is water. And water has some very unique properties. It's the most common compound of Earth, H2O. And one term that you need to know is specific heat, the amount of heat energy required to change the temperature of a substance, and in this case, water. A term that you're probably most familiar with is what we call the calorie, the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. That's a calorie. Okay, now, water is different states. It can be frozen, it can be liquid, it can be a vapor. And for water to go from one of those stages to another, you either have to absorb energy or liberate it, free the energy. And the amount of energy has to be enough to affect the hydrogen bonds, the H2 bonds in the water molecules. And when that happens, the water will either come together, become more dense and freeze, or the molecules will break apart and it will become vapor and will rise up. Now, this relationship between water and heat, that's the driving force in producing weather, this exchange of heat. It provides about 30% of the energy that powers the general circulation of the atmosphere. Now, we call these changing of states a phase change. Okay, so it involves the absorption or the release of what we call latent heat, and that includes freezing and melting, or condensation and evaporation. Okay, so this for vapor and for liquid and ice. Okay, so this is all in the book. So go in this and pay close attention. What we're mostly interested in is this, solid to liquid to gas, and gas to liquid to frozen. That's usually how that, how the things we're most concerned about. So make sure you pay attention to that in the book, okay, and also in the animations. Now, if you absorb heat energy, that's as latent heat, you melt, or you vaporize, or you evaporate. If you release heat energy as latent heat, you are condensing or you are freezing. So know the processes where think of an ice cube. You're absorbing heat, so it's going to melt. And if you add enough heat, the melted water will then vaporize. On the other hand, if you remove heat, the liquid water will bond together and will freeze. So you're either releasing or absorbing. So know the differences between the two. Now, we can measure, for this chapter, what we're interested in is water in the atmosphere. And we can measure this. It's what we call humidity, the water vapor in the air. And it's also a function of the temperature. The most common way you've probably heard this is what we call relative humidity. It's a ratio, which is a percentage, the amount of water vapor that is present in the air compared to the maximum water vapor possible in the air at a given temperature. So if they say it's 80 degrees out and it's 50% relative humidity, that means at that temperature, 80 degrees, the air is containing 50% of its maximum. When it gets to 100%, that means the air is saturated. And if you add just another drop of water, or you start to cool it, then it starts to condense, and you're going to get dew. Perhaps if it's on the ground, you're going to get clouds. If it's in the air, fog, or it's going to rain or snow, precipitation. So 100% is maximum saturation. 0% is incredibly dry with air, no water in the air at all. So if the air is dry, the relative humidity percentage is low. If the air is moist, the relative humidity is higher. If the air cannot hold any more moisture, it is what we call saturated, and the relative humidity is 100%. So dry, low relative humidity; moist, high relative humidity. So think of it this way. Notice that the water vapor, it's 4 grams in each of these diagrams, each of these circles. Notice the temperature differences. Well, it's not showing them, but in the temperature, it's going to be warmer here and cooler here. So the cool air has a lower ability to hold heat energy. So that's about 100% relative humidity at 5 a.m. Whereas at 5 p.m., when the earth has warmed up, the air is warmed up, it has a much larger ability to hold water vapor. So that 4 grams now is only 25%. So the air at 5 p.m., in this case, at this temperature, could hold. Its maximum potential will be 16 grams, but it's only holding 4, so it's 25%. Here, because the temperatures are cooler, the air can only hold 4 grams, and there are 4 grams of water vapor, so it's saturated. The relative humidity is 100%. So if you walked out in the morning, you're probably going to see dew on the ground. And that dew is when the temperature hits what we call the dew point, the temperature where a given mass of air becomes saturated and condensation begins. And if it's below freezing, it's what we call the frost point, when the air is below freezing. But Go back one slide. So here, when it reaches this, that's the dew point. Temperature where the mass of air becomes saturated and it starts to condense. And notice they're inversely related, meaning that here's humidity, here's temperature. The higher the temperature, the lower the humidity. The lowest temperature has the highest humidity. So this is over the course of the day. So as the earth cools down, humidity goes up. As the earth starts to warm up during the day, humidity goes down. So here it is from noon to midnight, and notice the humidity goes up. Okay, so this is in your book, so pay attention to that graphic, okay? And here's this is May 2009, or just some random one I picked out, but notice this is the average total precipitable water vapor in millimeters in the air. So remember from last lecture, this is the ITCZ down here. Low pressure, air rises up, very hot, lots of oceans to evaporate water from, so the air is very, very wet. As we move further north, temperatures get cooler, even in May, so less capacity. Less evaporation, so less water vapor in the air. So there's less ability for rain and precipitation. And then when you look at the distributions of global temperature and humidity, for example, so this is the mean air temperature. And so again, here's the United States over here. The ITCZ goes right through here. And the equator, right here, it's 0. So temperatures are going to be warmer right through here. Then they're going to cool off as we go up in latitude. And notice their, humidity is kind of related to that. Where you have lots of water, lots of evaporation, warm air in the tropics, you're going to get lots of moisture in the air, so it's going to be very humid. The cold air, as we get closer to the pole, there's less sunlight, less evaporation, so it makes the air very dry, so humidity is very low. Now we measure it using this instrument, what we call a psychrometer. It's if you're in the labs, you'll get a chance to do this. It's a very simple instrument. It's got what we call a wet bulb thermometer and a dry bulb thermometer. You put a little moisture on this, and then really just hold it in your hand and sling it around, and you're going to get the ambient temperature in the air with this. But this one, it has to evaporate this water first, and so it takes longer. So you do it for a time, like a minute, and you're going to get this difference in temperature. And then you take that and you look at a table at the difference between the two temperatures and look at it on this table, and you'll get the humidity. Okay, so let's stop here for this one, and we'll get with atmospheric stability for the next chapter.